Hello everyone, welcome to this video. In this video, we are going to learn about the Leaky integrated and fire spiking neural network using OpenMathAI. So, let's get started. What is a LIF SNN? A Leaky integrated and fire spiking neural network is a type of spiking neural network designed to process information using neuron-like electrical spikes. Unlike traditional neural networks, which continuously pass numerical values between neurons, a LIF SNN represents information through discrete spike events. In a LIF neuron, incoming signals are accumulated in the neuron's membrane potential. At the same time, the membrane potential gradually decreases, or leaks, over time. When the membrane potential reaches a predefined threshold, the neuron generates a spike and its membrane potential is reset. During prediction, the input signals activate different LIF neurons in the network. The neurons integrate the incoming information, generate spikes based on their membrane potentials, and propagate these spike signals through the network. The resulting spike activity is then used to calculate the final prediction. We will use a gesture recognition dataset for the LIF SNN model. This dataset contains 500 data samples. The input features are event X, event Y, and polarity, and the target output is gesture ID. The event X and event Y values represent the spatial positions of the detected events, while polarity represents the type or direction of the event change. The gesture ID identifies a corresponding gesture class. During training, the LIF SNN converts these input values into spike-based neural activity. The LIF neurons integrate the incoming signals over time, apply membrane leakage, and generate spikes whenever their membrane potentials reach the firing threshold. The network learns a relationship between these spike patterns and the corresponding gesture ID. Once the model is trained, OpenMathAI uses a learned spiking behavior and network parameters to predict the gesture ID for new event-based input data without retraining the model. So, let's get started. Open OpenMathAI. Click Create New Project. Enter the project name as LIF SNN. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Enable the dynamic case states, because LIF is a dynamic model. Configure the dataset by specifying the inputs, feedback states, and targets. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Feedback allows the previous reservoir state to influence the current state, enabling the LIF SNN to remember recent information. This short-term memory helps the model capture temporal dependencies and improve predictions for sequential data. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There is one more feature, signal diagnostics. There is a free columns. First one is column its tell which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's OK, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the LIF SNN model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration. Test data split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also another feature is added that is train from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, Root mean squared error, the square root of MSE. Our MSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R-squared, RMSE, and residual errors. Model accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95 accuracy, almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, comfortable, compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is Deselect and select all trained model for export. Click View Curves. You will see the diagram of parity, residuals, and residuals histogram and predicted output. Click Math and Code Preview to view the mathematical model generated by OpenMathAI. The complete Leaky integrated and fire spiking neural network architecture, generated source code, and training details. Open the Math view to visualize a complete LIF SNN model. Maximize a window and scroll down to see the input layer, recurrent reservoir with 400 spiking units, readout layer, output prediction, the feedback recurrence path, and a complete network structure. The visualization shows how input features are converted into spike signals, processed through a recurrent reservoir, and passed to the readout layer for prediction. The input layer sends the scaled input features to the recurrent reservoir, where 400 LIF neurons integrate spikes, fire when the threshold is reached, and learn temporal patterns through recurrent connections. The readout layer combines the reservoir states with the current inputs to generate the final prediction. The skip path directly connects the input to the readout layer, while the feedback path preserves short-term memory by allowing previous reservoir states to influence the current state. After training, OpenMathAI uses a learned reservoir dynamics and readout parameters to predict outputs for new input data without retraining the model. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format. ANSI, MCU Fixed Point C, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.